I'm Lars, and many years ago I used to work as a reverse engineer for the Norwegian CERT, and I remember it was very stressful. So they would tell me Norway is under attack, and you have to reverse engineer this binary. So I remember like going into panic mode and sitting single-stepping through all the debug like a crazy person, and my process was very like manual at the time, and I would say a little bit chaotic. And then in 2009, I joined a Norwegian antivirus company, famous for creating the first ever malware sandbox. And the guy who wrote this actually started his work all the way back in like the late 1990s. So I was working on the part of the antivirus stack that removed malware once we detected something. And that's how I kind of got into rootkits. Because the most difficult malware to remove is kind of the rootkits. So I did rootkit detection for a while. And I did some anti-rootkit technology for like the on-demand scanner, so it could detect hidden files. And then when we did the second generation of the malware sandbox, I ended up writing rootkits. So why would you write rootkits? Are you not working for a serious company? And the thing is, malware sandboxes are quite effective at detecting and analyzing files. So therefore, the malware authors typically try to evade us. And they do that typically by looking for signs of something that differs between like a sandbox environment and the real environment. So my approach was to create like a rootkit to basically hide our components on the system to kind of trick the malware into running. And I learned after like working with malware technology or sandbox technology for like 20 years that this is a very difficult problem. And if you've studied computer science, you might have heard about computability theory, more specifically about the halting problem. So the halting problem is something like this. Given a description of a program and input, decide if it finishes or runs forever. And this is kind of a simple yes or no answer. And then there's this guy, Alan Turing, maybe you heard of him, proved that a general algorithm for all possible program input pairs cannot exist. This was proven in 1936, so it's a long time ago, before the internet. And furthermore, the halting problem is what we call undecidable, which means it's like super hard and impossible to create like a generic algorithm to solve it. Now I'm going to argue that the sandbox evasion problem is likely a variation of the halting problem. And I'm going to do this. I figured since we were in a university, I was trying to make something like super academic. So I have this very academic approach, where I'm trying to basically transform the halting problem into the sandbox evasion problem. So we start with the first part of the halting problem, given a description of a program and input. This could be translated into given a binary file, because basically the binary file we can decompile, and that can be sort of our description of the program. And we don't really know the input, for the most part. And then the last part of the halting problem could be decide if it finishes or runs forever, could be transformed into decide if it terminates early or runs intended behavior. So it doesn't need to be like this, but very often the malware will kind of check if it's running in some type of sandbox, and then very often it will just terminate, or at least avoid doing whatever like malicious behavior it intends, so that we don't detect it. That's like the gist of it. So this would probably mean that the sandbox evasion problem is likely also undecidable. Super academically proven. The thing is, for this project, I was interviewing some malware and threat analysts that work for various cybersecurity companies. Since it's been a long time since I actually did this as my day job myself. And kind of understanding a little bit about how they approach reverse engineering, what their workflows were, and like what their pain points were. And it turns out that most of them relied on sandboxes in some way or another. They see a lot of files, and so it's very easy to kind of use this, some type of sandbox for like an initial analysis. The challenge is that very often they don't get the results they want. So if for like there's some infinite many reasons why some program wouldn't run in a sandbox. So very often they just don't produce any information. And if they don't produce any information, then they tell me that kind of manually reverse engineering is slow, which I can, well, at least it's slow for me as well, so I understand. So it can easily take them a few weeks just to analyze a single file if it's like some type of a little bit complicated. And then also we have like lots of like false positives and false negatives, and just in general too many files to worry about. So that's kind of the challenge. So I'm asking the question, can we make reverse engineering easier and faster? So I came up with this idea of, let's call it a reverse engineering paradigm that I call iterative reverse engineering. So in this way of reverse engineering, you will basically start with doing a quick static analysis. So you look at like the strings, what type of file it is. I want normally just to get all of the disassembly and the decompile code so I can kind of scroll through it, just to have an idea. This is basically how I used to work as well when people would send me files complaining that the sandbox didn't work. They would tell me, oh, your sandbox is bad. This malware doesn't run. So it's kind of like I like to see what code it is before I make up my opinion on how it should be running. So then you use this information that you retrieve from your static analysis to basically tweak your dynamic analysis. This means that if you can study the file to a level that you can maybe recognize that it requires some command line parameters. Maybe you can see like what type of file, at least you know if like a 32-bit file or 64-bit file, it will tell you something about the environment in which it should run. So then you run the sample, and then take output from the dynamic analysis and use that to kind of refine your static analysis. So typically, like in a sandbox, you can kind of get this with events, which would be typically like API calls, API like parameters and stuff, and some traces, which should tell you like what type or what code has been run. So you can kind of recognize that if it's terminating early, you can kind of understand maybe where it stopped. So that now can become your like a focus point of how you can force the malware or force something to go down a different branch. And as you kind of make new discoveries, you kind of just iterate on this until you have the required result. So it's very rare that you need to like totally reverse engineer every single bit in a file, because that will take a very long time. So hopefully you should have some type of idea of what you want to figure out. Someone's probably asking you some questions about this file. Is it suspicious? What is it? What is it not? So you kind of just iterate until you have the answer you need. So this is kind of my amazing illustration. You start with some type of static analysis, and this will tell you kind of how you should tweak the setting for your dynamic analysis. And then you use the events and traces that come out of dynamic analysis to kind of refine your static analysis. This means that basically you should be able to kind of rename your functions and stuff based on dynamic analysis to kind of help you understand what different functions do and so on. So I'm making a web application to try to enable this. And it should come as no surprise, since you are in r2con, that the static analysis is based on R2. And it's basically, we want to, as I told you, I like to just read the code starting from the entry point as my first step. And I've experimented a little bit back and forth, and I want to have like a UI where I get all of the disassembled code so I can kind of scroll through it. Maybe later we can add some filtering and stuff, but essentially I want to disassemble and decompile all code. And I also talked with some people who know something about UX. This is the first time I ever did a UI in my life, I think. I think this is my third iteration of trying to build like a like a web UI that makes sense and looks decent-ish. But the thing is, like, the good UX kind of boils down to responding fast. That's what they tell me. So it means that the opposite of good UX, like bad UX, is something that if you click something and that it takes forever to respond. So maybe it's like just it's annoying spinner and things like this. This will annoy the user. Whereas if you can make something fast, that means the user will be happy. And also it means that they can reverse engineer faster. And we know that disassembly and decompilation is basically CPU-bound processes. It means that for the most part, the CPU should be the bottleneck for how fast we could do it. So I'm trying to look into basically how we could use multi-threading to speed up, or something akin to that, to speed up the process. The challenge now is that R2 is single-threaded. So I have some ideas in this space. Basically, I rewrote the backend lately to use async Rust. So I have some ideas I might want to experiment with. But for now, at least, I'm just basically trying to split the work of R2 does into multiple processes. So auto-analysis isn't really, I didn't find like a nice way to split it out yet. So now we kind of do auto-analysis single-threaded, but then I try to do as little analysis as possible. And the requirement is you kind of need to get decompilation working. So essentially it means, in our case, that whatever R2 Ghidra needs, we need to kind of just do those steps in the analysis. And then I'm running like a subset of the analysis commands that normally runs during auto-analysis. I mean, R2 is kind of logical, so if you go into like the AAA command, you're going to see like the various subcommands that it normally does. There's lots of different ways that it can do auto-analysis. The most important operation is AAC, which is basically like a flat disassembly of the file and looking for call instructions. And the idea is if you find a call, then probably it's a function. These other functions I normally used to, this is like the most helpful command in R2 that Pancake ever showed me. So if you ever worry about anything like what a specific command does, or if you want to find some commands, then you can use this interactive help command. This is the best command. Okay, so once auto-analysis is completed in like a single thread, I save some meta information that I want to use later. So kind of wanting to branch out in multiple processes. I had a look at the project code to see how that was done there. So currently I'm using these commands to, the first one, AFL, will generate the list of all functions. And then I dump all of the flags. And then I dump all of the cross-references. At least for now, this seems to be sufficient. So I kind of basically just put all those R2 commands in a file. And then each of the multiple processes that will run later will basically just load the meta information into new processes. And basically, that's the way we can run things in parallel. So for now, I'll just do basically disassembly in one process and decompilation in another process, which is okay for like smaller binaries, but I was looking into finding some demo for this conference. I was looking at like some Go binaries, for instance, that statically link the runtime. So they become like 3 gigabyte files. And in those cases, it takes a long time to kind of just go through and decompile everything. Another thing I want to point out is that with our approach, we constantly need to rebase the binary. Because I want to kind of compare the sample with whatever is information I get from dynamic analysis, and do that over and over again. And it means that every time the sample is loaded, it will likely load at a new base address. So rebasing needs to kind of happen automatically. because it's some of the most really annoying things. I know if I need to do this in my head, then I always get it wrong. I get kind of confused myself. So that's kind of a thing I might want to look into later. I didn't find like an easy way to do this yet in R2, so currently we actually just reanalyze the binary each time it's loaded at a new address. So this is one of the very many things I need to find a better solution on at some point. And then to generate events, we use Frida. Like lots of other people. So we use Frida to basically hook APIs. I like Frida because it's so flexible. And so just hook APIs, output the fact that they are called and which parameters they take. And then I also use the stalker module to generate traces, to get me like an idea of what code has been run. So the backend is written in Rust, so we just use the C API, the SDK, directly, and then I'm running a Frida server in the virtual machine. And then I enable this hypervisor debugging thing that I've presented on before, which basically it's running on the host in the form of an R2 debug plugin, and it has like access to the physical memory of the virtual machine, and it controls the CPU essentially of via the GDB stub in QEMU. So this means we can single step anything, we can basically debug anything inside the VM. And it also enables something, a small little feature that I kind of wanted, which I call automatic load phase analysis. So the thing is that very often, if you drop a sample into a sandbox and it doesn't run, very often it's not because it's evading, it's because it's like missing a DLL, or it might be corrupted, and things like this. So what I do is basically, as I'm using Frida inside the VM to load the file, I essentially also connect my debugger and then just place a breakpoint on the entry point and then let it go. And if it hits the entry point, at least I know it's starting execution from the entry point. So I can kind of rule out if there's any issues that happen during loading. And as I said, it also enables us to basically do interactive debugging. I still haven't completed like the web UI for this, so currently I'm running like a terminal thing in the browser, and just run R2 directly, which I will show you in a second. Oh no. So let's have a look what we are doing. So I prepared like a few quick demos of how this looks today. So just going to start by uploading a file, my passion.exe, and then it creates like a new analysis for me. And you can see right now over here it's decompiling it. That means that auto analysis has completed, and we also have already gotten all of the disassembly. So you can, as this is happening, you can kind of just browse through the disassembly of like the entire file. And now you can see decompilation is also completed. This is kind of what I want to do sometimes. I can just scroll through things. There's like some strings and stuff might be interesting to look at. Imports from various DLLs. I mean, I do have like an R2 terminal here using Xterm, so you can kind of drop into an R2 shell. And then one thing I kind of find interesting is what I'm playing with is I have this like dual mode thing that I'm playing around with. Because this is from when I'm actually writing code myself. I always have this split screen concept. So I typically look at some code I've written before or someone else has written on the right, and then I type my code on the left. So I'll try to, and then with this, Yes, no problem. For me, it's like if I'm looking at obfuscated code, then typically I prefer to read the disassembly. And if I'm looking at something that is nicer, then typically it's faster to look at the decompile code. So what I'm doing here is basically I'm storing the virtual address inside. This is a Monaco editor, by the way. It's amazing. What happened to Microsoft? All of a sudden, they become this really cool company that releases open source. And so basically, this enables you to kind of scroll down on the decompiled code, and you see like the corresponding assembly at the same time. They basically synced up based on addresses, which I think is interesting. And then we can basically just start this VM. Since we kind of did our quick static analysis, we know it's like a 64-bit executable. This will boot up a VM. And eventually we'll see some whatever event Frida gives us here. So you can see it's loading the program. It's loaded our Frida script, and then it's telling me it's running from the entry point. Maybe that's too small for you to see. Did I screw something up? Oh, here we go. Something's lagging. And then yeah, basically you can see at least it started running from the entry point, and then it terminated. So not a lot going on yet. So this would be the situation where you didn't really get any events out. This is quite a very simple example. The idea is that you can kind of quickly look at the decompiled code and figure out that in this case it has like an if statement. Param 1 is 2. And you can understand that this is it's basically a command line program. So it just checks if argc is 2 or not. And then there's a return down here. So basically means we need to give it some argument. So we do that, kind of tweak our dynamic analysis, and then run this again. And then something else happened. It logged me out. How rude. And we see now there's actually some more events reported to us from Frida. So we can see that there's a call to exit Windows, EX, which is obviously why it logged me out. Actually, 2 calls to exit Windows, just to be safe. So this means, okay, we have actually, at least we have gotten further into like this execution. So if I'm lazy now, I can kind of just run a different Frida script and just enable some tracing. So in this case, I just wrote like a special trace script to start tracing from main. Just to make the demo a little easier. So we select that and kind of load it again. And then logs it out again. So same behavior as last time, which is to be expected. And now we have some more traces from the Stalker module. So we see like the same 2 API calls. And now we can kind of compare the traces from Frida with the sample. So kind of side by side, and then syncing the views. I can kind of, so if you look at, I'm just going to scroll down on the left side, and you can kind of follow the code flow on the right side. You can kind of see what's going on. So it's going into this if and it's actually executing the if. And then there's another if, and then it's calling this function at something 1010, and that is the thing that is calling exit windows. So probably this is not the function we want to call. So you're going to check this if, and it's checking param2 plus 8, which is the first command line parameter, and it requires like the first character of this essentially to be 0. ASCII 0. Okay. So then you know that. You kind of go back and change the argument to be 0. Run it again with the same tracing. Okay, so it's still signing me out. But now, doing the same approach, we can kind of see that this was no longer taken. And instead, it's coming to this next if. And so you can see like, okay, so it's doing whatever this madness is, and it's running this else thing, which again ends up in exit windows EX. But this is kind of like how I imagine you can kind of just iterate on it and tweak things as you go, and you know, write your customized Frida script for the specific sample and kind of to speed up things. So I wanted to show you just quickly one more demo to just show you how this hypervisor debugger looks. So let's, I can just upload it again. So let's upload a new demo file. So again, it's doing analysis. This file was like shorter or smaller. So it gives me access to all the decompiled code quite fast. Start this VM and let it boot up. And then while it's booting up, we can have a look. Things. Sometimes I don't even know what I'm looking for when I'm doing this. It's kind of like, I'd still like to look at it to see if it's something I recognize, or you get like an idea of what it might be, or maybe, and what it's definitely not. In this case, I have like a Yara rule also, that sometimes can be helpful if you just to recognize aspect of code you've seen before. So I have like a Yara integration. Now you can see there are some funny things, funny strings in here. So there's at least something to expect. Okay, so this program is running now, and it's Obi-Wan Kino telling us the forces. Okay, that's interesting. So let's see. I'm a little bit confused now. I don't really know what I'm looking at. Is it? I mean, maybe this was not like the behavior I was expecting. So I'll run it again with. Let's do this tracing with Frida, just to kind of do the same thing again with enabling Frida tracing. Let this go. Just yep. And this time, the idea is that I'm going to use Frida tracing to kind of help me locate interesting code and kind of give me some hints at where I should look. Okay, so the same experience, it says the forces. And now we have like a lot more traces this time. It's actually tracing all the way from the entry point. And then kind of just scroll down and you can see, okay, all of this code was executed. And then eventually we get here. And so this, I'm missing a few events now, but basically it gives me an idea of where in the code how far it ran. So now maybe this now can become the code I want to look at. And if I read this code, it's basically calling get computer name, which is used to, in this case, it's used to get the Windows domain, and then it's checking for like if this is like it's the bank.com domain, and then there's like an if-else after. But you get the idea. It's basically maybe some malware wanted to only run on like a specific domain or something. So I figured I should show you just basically using the debugger to kind of just force this else branch, which is like a different approach. Obviously, we could use Frida and just fake the results as well. So you kind of have multiple options. So if you look at the assembly, and then basically it's a call get computer name, and it's checking for errors, and then yep, there is a string compare, and then it's testing the result of the string compare here, and then this is the if-else essentially. So if I go back and then iterate again, this time I will use my hypervisor debugger to basically freeze the VM on the entry point. So run it again, and then I do my thing in the beginning to make sure it's just exactly the same kind of process as we did to make sure that the entry point is running. This time I'm just not continuing after. So this means that now it's frozen. Should be. And then it's giving me the option of using this debugger. This is how the UI looks for now. I'm still kind of using a Monaco editor for everything. But this information is retrieved via the debugger, so it's basically carved out from the outside, which means you can see all of the processes that runs on the system. And then you can see kind of all of the threads for each process, like the memory modules for each process. So you can see movie exe is loaded Frida to improve it. Like the memory maps, and then also you can see things like all of the drivers and stuff. And then I have this R2 debugger terminal that enables me to kind of interact with it. So if we seek to rip, we are now at the entry point. And then from this analysis, I located this, basically the string compare. So I'm just going to go in here and just copy the virtual address of this instruction. And then place a breakpoint on that address. And let it run. It should hit, but something's wrong. No. Maybe that's, maybe I forgot that. Okay. That's true. It should. It still works with Soccer. It should. I think just maybe. Okay. Let's try it again. Maybe I did something wrong. That's true. You can disable Frida, I suppose, but I'm not sure if it should matter. Okay. Let's see. Try it again. Yeah, there were some issues. I was running this demo in my hotel room, and there was some tricky things. Stressed me out a bit, but this is it's fine. Let's try again. See if we can make it work. Okay. Okay, so we're at the entry point. Connect R2. Get this address. Seek to it. Place a breakpoint. And now it worked, at least. So the breakpoint is hit. In this case, I just want to force the else branch just to show you that it's like displaying a different message box. So you can see rax is -1. So if you just set rax to 0 and let it run, then it will say, "Are you daddy?" So it's kind of like how I envision we can kind of change the behavior of whatever is running inside this sandbox from the outside. Okay, that's it for the demo. So thank you a lot. I do have a Discord that you can join if you go to codetracer.com. I'm also on R2's Discord and Telegram. So if you are interested in kind of contributing or helping out with this project in any way, let me know. And enjoy the conference. Thank you.
Any question? We have some minutes. Oh, have a question.
Are you fully rebooting the DVM every time you do a new run?
Well, I experimented a little bit with this. So as I told you, in last last year, first I kind of decided to rewrite the front end because I wasn't quite happy, and then I decided to rewrite the back end. So before, in the old back end, we used to always require you to have a snapshot that you will revert back to.
Yeah, that was what I was thinking.
And then I was experimenting a little bit with this. For now, I kind of want to have both available because it saves me a lot of logistical challenges if I don't have to keep like a huge tree of like big snapshots. So for now, but you don't need to, but you can. So in the first demo, I showed I run it multiple times, but that's just without actually reverting it. So obviously, if you have some type of malware or something, it can screw up the system, and then you might want to revert. But it's also really much faster if you don't require the user to always revert back to a snapshot. So I just haven't gotten around to having snapshot support so far.
Thank you.
Thanks.
Any other question? No? Thank you. Big applause.
Thank you.